Good afternoon. My name is Mitchell Power, and I'll be talking today about some research we've been doing out in the Fish Lake Basin. I have to give a big shout out to my collaborators from here from the University of Utah, Andrew Burnell, Jesse Morris, also Michelle Carter from Los Alamos Labs, Leslie Anderson from the U.S. Geological Survey, and Mark Abbott, and Jamie Bornlocker from University of Pittsburgh, and then Dave Marchetti from Western Colorado University. And I'll also acknowledge the dozens of students that have been helping with this research along the way. So today I'll be talking about history of Aspen as we've been learning about it from the Fish Lake Basin and try to offer some perspective on that. And I think it goes without saying that many of us have come to learn that Aspen is under threat. There's multiple threats in today's changing climate. We have elevated droughts that are potentially causing sudden aspen decline. We have increase in the severity and area of wildfires. We have challenges with herbivory and ungulate and artiodactyl herbivory of aspen, both in the juvenile stage and adult stages. And of course, we also have human activities, which range from things more direct, like logging and habitat fragmentation, to some of the indirect consequences of fire suppression. And so I'll try to tackle many of these from some of the evidence we have coming from the work we're doing. One thing I won't really be addressing today is some of the disease impacts to aspen forests. And so a little bit about aspen ecology. Most of you probably know this, but aspens are found in an incredibly widely distributed geographic range. They occur all over North America, in boreal forests down through the Intermountain West. They're associated at some of the lower elevations with arid shrublands, and at the higher elevations with wet spruce fir forest. Aspens generally tend to support high species richness. Some of the work done here at the University of Utah by Bill Anderegg has captured some of the differences in understory richness in the aspen communities. Also, many of you know aspen have various strategies for regeneration. They are quite well known for their clonal structures and the ability to vegetatively resprout through suckering. Of course, they're also prolific seed producers in the Intermountain West, and these seeds can be quite small to the eye, less than a millimeter, and allow for range expansion. Some of the work that's been going on currently by Karen Mock and her students up at Utah State has been looking at some of the relative proportions of male and female aspen. Of course, it's a monoecious species. It tends to have about a 2-to-1 ratio of males dominating over females in the Intermountain West. And what's interesting about that is the male aspen clones, of course, which Pando is one of those male aspen clones. They tend to persist longer and they expand more than the female clones. And then in addition to that, you tend to find more male aspen trees at higher elevation and more male trees when annual precipitation is higher. And so with that, what's the motivation for this research? Well, as the urgency around aspen has increased over the last couple of decades, we began to ask, what are these threats, and are these threats unprecedented? How has aspen responded in the past to some of these types of challenges? And so we'll be kind of looking at these much longer timescales today. We'll be bouncing around this ecological scale back into what I like to call the quaternary scale. So we'll be looking at changes over thousands of years. But there's a few other pieces that are relevant here that, the regeneration of aspen may be hampered by the lack of disturbance. I think most people would agree on that. And that browsing impacts on relatively short time scales can really suppress the regeneration and ultimately cause reduced recruitment. Species richness in aspen forests, especially the understory, tends to decline in an unhealthy aspen stands. And then, the resulting shrub, grass, and conifer-dominated vegetation shifts that we're seeing in some of these aspen forests tend to result in a lower level of species richness. So with that, take you to Fish Lake, where we've just recently been out for some more field work. We were there over the last weekend in February, out on the ice, about 10 inches of ice this year. Each year it's a bit less. This is our third field campaign. Basically, this year we're trying to extend the record a bit back in time. But those are some of my colleagues from Pittsburgh, Mark Abbott there, running the UETech coring system, which allows us to work in 100 feet of water and then taking core samples, as you see in the bottom right there, from deep into the sediments at the bottom of the lake. I also have my colleague Dave Marchetti, who's at Western Colorado. He's been working on mapping some of the glacial features out around the Fish Lake Basin. And so we're starting to combine some of these lines of evidence of the long-term history of Fish Lake. And so to have an understanding of what kind of history, we need to develop an age chronology. And so what I'm showing you here is the composite, what we call age depth model. And so on the y-axis at the top is the depth of sediments, or now just over 18 meters of sediment from the bottom of Fish Lake. And then the chronology based on a suite of lead-210 for more recent, and then radiocarbon ages, both in black circles and purple diamonds. And then the red triangles are tephra ages we were able to define in the core. And if you look at the green line at the bottom here, what you're really seeing is an index of relative organic content over this record. And we now have about a 60,000 year record of Fish Lake, which is mostly captured during the last glacial period, and then around 10,000 years ago, moving into the Holocene. And so when we sample these records, we tend to sample them contiguously. We're taking these samples in the lab, we're chemically treating them to extract biological proxies, and in some cases charred plant material, in some cases microscopic pollen. We process those samples, get them on the microscope, and quantify their abundance. And so you can see the top of the slide here, there's some images of typical conifer pollen, large grass grains, and then some of the morphological types of charred plant material. And so when you think about herbivory as one of the factors driving Aspen changes in expansion, contraction of their range, one source we can look at are the archaeological records with faunal remains. I did a little digging into some of Grayson's work, and he captures quite a bit of elk fauna in archaeological sites, but that tends to cluster towards the late Holocene, the last couple thousand years. It kind of provides limited evidence of the ubiquitous of herbivory. Additionally, we can turn to a dung fungal spore called Sporamiella. It's an obligate coprophilous spore, and it occurs in wild herbivore dung, and it's been used by paleoecologists for many decades as an index of herbivory. And so with that, let's look at a little bit of our preliminary data. This is unpublished data, but this is now showing, I've just selected a few of the pollen types here, sagebrush running across the bottom from 60,000 years to present, grasses represented as the poaceae, and then spruce. And what you can generally see is that sagebrush has dominated the story for much of the glacial period. It's probably been very much like a sagebrush grassland with elements of spruce. In most paleoecological records that span this glacial period, it's very common to see this shrub steppe grassland, which if you were to walk around the ridge lines above Fish Lake today at 11,000 feet, this is exactly what you'd see. You'd see this spruce open steppe grassland. Now, at the top of this time series, I have the Sporamiella spore. So this is the dung fungal spore. And what's interesting is it shows up for much of the glacial period from about 60,000 years to present. Of course, you have to remember, as you move back in time, we're moving into a time with many, many more ungulates and herbivores and browsers on the landscape, horses and camels and bison, to name a few. Many of those species went extinct at the end of the Ice Age around 12,000 years ago. But the Sporamiella that we see there is a continuous evidence of potential herbivores moving around Fish Lake Basin. But I really want to focus here on the aspen story. So this is Populus tremuloides. This is likely our best candidate since there are potentially other Populus wind dispersed pollen types in the region, but aspen, if you look over this long record, has been mostly present for much of the glacial, coming in and out of abundance. Aspen pollen can be a bit difficult to find in these records, and so its absence isn't clear evidence of not being present, but we do see a significant jump in aspen pollen or Populus pollen in the last 10,000 years. So let's shift our time frame here and look at a little more closely time since the last ice age. And so in the last 18,000 years, we see that there's been an increase in fire. So the index I'm showing you at the bottom of this data series is 18,000 years of fire record. So this is charred plant material. And then I've mapped just above that the evidence of Populus pollen in this sediment record. And what you can generally see on these long millennial timescales is that as fire increases, aspen's been increasing. But if we take all 73 pollen species that were identified in this record, and we apply what's called a rare fraction index method to look at diversity, what we see is generally as aspen's been increasing, diversity has been increasing in the system. And then I just want you all to be mindful of the changes in summertime temperatures. As we move back about 10 to 11,000 years ago, we had, in terms of watts per meter square, an anomaly of 20 to 25 watts per meter square greater in the summer months. So that higher energy could potentially have driven up more wildfires, might have limited the initial expansion of aspen, and then as that insolation or heat energy anomaly came down, we see the increase in the expansion of aspen. And then if we step out and take a much broader view of what's happening here, so in this case, what I did is I took the Fish Lake data, and then I went into a publicly available database called Neotoma. It holds much of the paleoecological data from North America. And so I started to query other sites with aspen. And so what I'm showing you here are 14,000 years of multi-site signals of aspen. So that bottom curve is showing a general trend that aspen increases over time. You do the same for multi-site charred plant material, and you get kind of an interesting story, you increasing over time. So you could almost make an argument here that aspen and fire have a kind of long-term partnership. And then as you move up in those data series, second from the top is the index that we use for calculating prehistoric abundance on the landscape. And that in this case, what we're looking at is the number of archaeological sites with radiocarbon dates, and this is used as an index of relative abundance of people. This is some work put together by Brian Cotting, but what it's showing is in the last couple millennia, we have an ever increasing presence of people on the landscape. And this is particular to the Fish Lake region, this index. And then finally at the very top, you can see a new climate record just come out by Matthew White Lachine et al. In 2023. And he used a speleothem from a cave in the Grand Canyon to show changes in moisture over time. And what you can see is in that early Holocene, so from about 14,000 to 8,000, you have an intensification of the monsoon that's probably driven by this higher than normal summer insolation. And so things were wetter. If you look at the regional fire, it's likely that increased monsoon moisture in the Intermountain West, particularly the Southwest, could have driven down some of the summertime fire activity, but also probably created an opening and opportunity for aspen to expand on the landscape. And then I want to just give you a couple other examples from some of our team that have been working on this question for a while. This is work by Jesse Morris and his colleague Justin DeRose on Sugarloaf Pond in southwestern Utah. What they find is a negative correlation between fir pollen and aspen pollen. And what's really interesting is when you apply evidence of fire, you tend to increase your fire activity as aspen switches from a cereal to stable component of the watershed around Sugarloaf Pond. And so really interesting here to see how large severity fires, like that one detected about 1,700 years ago, is potentially a threshold or mechanism to shift to a more stable aspen community type. And then lastly, I'll point out some work done by many members in our team. This was led by Michelle Carter, and this was looking at evidence around Fish Lake of human population and landscape manipulation. And what we found here is in this lower time series, you're seeing the incidence of radiocarbon dates as a population metric for the Fish Lake Basin. And then above that, you're seeing the abundance of burnt plant materials over time. And when you run these data along with some climate data and some of the other pollen data through a general additive model, it prescribes the proportional change from different variables. And in the case for certainly the last 1,200 years, and definitely within the 1,400 to 900 calendar years ago, changes in human population seem to be the dominant driver next to wildfires for shifts in community dynamics around Fish Lake. And so in summary, I would just say that aspens have been part of the Fish Lake and Western US ecological communities for at least 60,000 years. The historical processes that impact aspen ecosystems resilience through time, which include natural fires, herbivory, and even prehistoric human activities, are part of that legacy of aspen. Thresholds and tipping points that can transition aspen from a cereal to a stable community type are certainly evident in the past and potentially one of the areas of concern for the future. And then finally, I think fire is a critical mechanism to maintain aspen. It's a bit of a Goldilocks idea. You can't have too little or too much, but just the right amount of aspen can help maintain the long-term persistence and diversity in aspen communities. And with that, I'd just like to thank many of my colleagues that contribute to this work and the students involved that spend hundreds of hours in the lab counting pollen and counting charcoal and documenting mineralogical changes. And so with that, I'll be happy to take some questions. Thank you very much.